actually encrypted using that thing you probably know in URLs known as HTTPS, where the S literally means secure. More on what the HTTP means later. If it's email, the number might be 25 or 465 or 587. Like, these are the kinds of things you Google if you ultimately care about. But if you've ever had to configure like Outlook or even Gmail to talk to another account, you might very well have seen these numbers by typing in something like smtp.gmail.com and then a number, which is only to say these numbers are omnipresent. But they're typically not things you and I have to care about because servers and computers nowadays automate much of this process. But that's all it takes ultimately for Phyllis to get this message to Brian. But what if it's a really big message? If it's a short email, it might fit perfectly in one single packet, so to speak. But suppose that Phyllis wants to send Brian a picture of a cat like this, or worse, a video of a cat. It would be kind of inequitable if no one else could do anything on the internet just because Phyllis wants to send Brian a really big picture, a really big video of a cat. It would be nice if we could kind of timeshare the interconnections across these routers so that we can give a little bit of time to Phyllis, a little bit of time to someone else, a little bit of time to someone else, so that eventually Phyllis's entire cat gets through the internet. But in terms of fairness, she doesn't monopolize the bandwidth of the network in question. And this then allows us to do one other feature of TCP/IP, which is fragmentation, where we can temporarily, and Phyllis's computer would do this automatically, fragment the big packet in question, or the big file in question, and then use not just a single envelope, but maybe a second, a third, and a fourth, or more. If we do that, though, we're probably going to need one other piece of information just logically on these envelopes. Like if you were implementing this, chopping up this picture of a cat into 4 parts, like intuitively, what might you want to put virtually on the outside of this envelope now? Yeah. The order of them somehow. So probably something like part 1 of 4, part 2 of 4, part 3 of 4, and so forth. So I'm going to write one more thing in like the memo line of the envelope here. I put some kind of sequence number that's just a little bit of a clue to Brian to know in what order to reassemble these things. And even more powerfully than that, this actually gives us this simple primitive of just using ints on these envelopes in these packets. If Brian receives envelopes like these, with numbers like these in the memo field, what other feature does TCP apparently enable Brian and Phyllis to implement? This is a bit subtle, but it's not just the ordering of the packets. What else might be useful about putting numbers on these things, might you think? What might be useful here? Yeah, back? Sorry, a little louder? If you missed something that was intended to be sent, if I heard that correct. So short answer, exactly, yes. So TCP, because of this simple little integer that we're including, can quote unquote guarantee delivery. Why? Because if Brian receives 1 out of 4, 2 out of 4, 4 out of 4, but not 3 out of 4, he now knows predictably that he needs to ask Phyllis somehow to resend that packet. And so this is why pretty much always, if you receive an email, you either receive the whole thing or nothing at all. Like sentences and words and paragraphs should never really be missing from an email. Or if you download a photograph on the web, it shouldn't just have a blank hole in the middle just because that packet of information happened to be lost. TCP, if it is the protocol being used to transmit data from point A to point B, ensures that it either all gets there or ultimately none of it at all. So this is an important property. But just as a teaser, there's other protocols out there. There's something called UDP, which is an alternative to TCP that doesn't guarantee delivery. And just as a taste of why you might ever not want to guarantee delivery, maybe you're watching like a streaming video, like a sports event online. You probably don't necessarily want the thing to buffer and buffer and buffer just because you have a slow connection, because you're going to start to miss things. And then you're going to be the only one in the world watching the game that ended 20 minutes ago when everyone else is sort of up to speed. Similarly for a voice call. It'd be really annoying if our voice is constantly buffered. So UDP might be a good protocol for making sure that even if the person on the other end sounds a little crappy, at least you can hear them. It's not pausing and resending, because that would really slow down that sort of human interaction. So in short, IP handles the addressing of these packets and standardizes numbers that every computer, your own included, gets. And TCP handles the standardization of like what services can be used between points A and point B. All right, this is great, but presumably when Phyllis sends a message to Brian, like she doesn't really know and probably shouldn't care what his IP address is, right? These days, it's like, I don't know most of the phone numbers that my friends have. I instead look them up in some way. And indeed, when you visit a website, what do you type in? It's typically not something dot something dot something dot something, where each of those somethings is a number. What do you typically type in to a browser? So a domain name, right? Something like stanford.edu, harvard.edu, yale.edu, gmail.com, or any other such domain name. And so thankfully, there's another system on the internet, one more acronym for today, called DNS, Domain Name System. And pretty much every network on the internet, Harvard's, Yale's, Comcast's, your own home network, somewhere, somehow has a DNS server. You probably didn't have to configure it yourself. Someone else did, your campus, your job, your internet service provider. But there's some server connected somehow to the network you're on via wires or wirelessly that just has a really big table in its memory, a big spreadsheet, if you will, or if you prefer, a hash table that has at least two columns of keys and values respectively, where on the left-hand side is what we'll call domain name, something like harvard.edu, yale.edu, and IP address on the right-hand side. That is to say, a DNS server's purpose in life is just to translate domain names to IP addresses, and vice versa if you want to go in the other direction. And technically, just to be precise, it translates fully qualified domain names to IP addresses. And we'll see what those are in just a moment. But again, all of this just kind of happens magically when you turn on your phone or your laptop today, because all of these things are pre-configured for us nowadays. So how can we actually start to see some of these things in action? Well, let's go ahead and poke around, for instance, at a couple of URLs here. Let me see. Let me switch over here for a second. And let me go ahead and propose that. Give me just one moment that we consider. Let me slide something around here. Give me a moment. All right. Let's see what we can actually do now with these basic primitives. If we now have the ability to move data from point A to point B, and what can be in that envelope could be, yes, an email, but today onward, it's really going to be web content. There's going to be content that you're requesting, like give me today's homepage, and there's content you're sending, which would be the contents of that actual homepage. And so, just to go one level deeper, now that we have these packets that are getting from point A to point B using TCP/IP, let's put something specific inside of them. Not just an email and a bunch of text, but something called HTTP, which stands for Hypertext Transfer Protocol. You've seen this for decades now, probably, in the form of URLs, so much so that you probably don't even type it nowadays. Your browser just adds it for you automatically, and you just type in harvard.edu or yale.edu or the like. But HTTP is just a final protocol that we'll talk about here that just standardizes how web browsers and web servers intercommunicate. So this is a distinction now between the internet and the web. The internet is really like the low-level plumbing, all of the cables, all of the technology that just moves packets from left to right, right to left, top to bottom, that gets data from point A to point B. You can do anything you want on top of that internet nowadays, email, and web, and video, and chat, and gaming, and all of that. So HTTP, or the web, is just one application that is conceptually on top of, built on top of the internet. Once you take for granted that there is an internet, you can do really interesting things with it, just like in our physical world. Once you have electricity, you can just assume you can do really interesting things with that too, without even knowing or caring how it works. But now that you'll be programming for the web, it's useful to understand how some of these things indeed work. So let's take a peek at the format of the things that go inside of these messages. These days, it's usually actually HTTPS that's in play, where again, the S just means secure. More on that later. But the HTTP is what standardizes what kinds of messages go inside of these envelopes. And wonderfully, it's just textual information typically. There's a simple text format that humans decided on years ago that goes inside of these envelopes that tells a browser how to request information from a server and how to respond from the server to that client with information. So here's, for instance, a canonical URL, https://www.example.com. What might you see at the end of this? You might sometimes see a slash. Browsers nowadays kind of simplify things and don't show it to you. But slash, as we'll see, just represents like the default folder, the root of the web server's hard drive, like whatever the base is of it. It's like C:\/ on Windows, or it's my computer on Mac OS. But a URL can have more than that. It can have /path, where path is just a word or multiple words that sort of describe a longer part of the URL. That path could actually be a specific file, we'll see, like something called file.html. More on HTML in just a bit. Or it can even be /folder, maybe with another slash, or maybe it can be /folder/file.html. Now, these days, Safari and even Chrome to some extent and other browsers are in the habit of trying to hide more and more of these details from you and me. Ultimately, though, it'll be useful to understand what URLs you're at because it maps directly to the code that we're ultimately going to write. But this is only to say that all this stuff in yellow refers to, presumably, a specific file and/or folder on the web server on which you're programming. All right, what's this? Example.com. This is the domain name as we described it earlier. Example.com is the so-called domain name. This whole thing, www.example.com, is the fully qualified domain name. And what the www is referring to is specifically the name of a specific server in that domain. So back in the day, there was a www.example.com web server. There might have been a mail.example.com mail server. There might have been a chat.example.com chat server. Nowadays, this host name or subdomain, depending on the context, can actually refer to a whole bunch of servers, right? When you go to www.facebook.com, that's not one server. That's thousands of servers nowadays. So long story short, there's technology that somehow get your data to one of those servers. But this whole thing is what we meant by fully qualified domain name. This thing here, host name. In the context of an email address, it might alternatively be called a subdomain. This thing here, top level domain. Probably know that .com means commercial, although anyone can buy it these days. .org is similar, .net. Some of them are a bit restricted. .mil is just for the US military. .edu is just for accredited educational institutions. But there are hundreds, if not more, top-level domains nowadays, some more popular than others. CS50's tools, for instance, use CS50.io. IO sort of connotes input-output. It actually is belongs, though, to a small island nation, a country whose country code is .io. And you see other two-letter top-level domains that are country-specific indeed. Something.uk, something.jp, and the like typically refer to countries. But some of them have been rather co-opted. .tv as well, because they have these meanings in English as well. Lastly, this is what we'll call the protocol. That specifies how the server uses this URL to get data from point A to point B. So what is inside of this envelope? Let's now start poking around a little bit more. What is inside of this envelope? It's essentially, for our purposes today, one of two verbs, either get or post. And if any of you have dabbled with HTML or made your own website, you might have seen some of these terms before. But these two verbs describe just how to send information from you to the